the very first thing you are told to try to do, because it seems like a tricky question, right? You have two variables, you need to swap them, and not everyone really realizes that they are allowed to declare temporary variables to use to perform the swap. So swap is the first topic we'll see today. And after swap, we are going to see more swap, clever things you can do with swap, even more clever things you can do with swap, and then the heap swap. So let's begin with swap. How do I write a function that swaps to variable? Let's start easy, and let's pretend we're swapping two integers. What do we write? Well, it's fairly easy. Void swap, int_ref, and we do the thing. So far, so good, right? Can you read the code? Is big enough? White background? Perfect. Okay, but we are in C++. C++ does have stud swap. So how could stud swap works in theory? Let's take another step. Let's make it generic. If you've been in the talk that was before in this room, you already know what does auto do here. This is a template. In C++20, this is a compact template, but if you're not used to it, just imagine template type name T, void swap, TT, okay? So this is a generic implementation to swap. Are we fine with this generic implementation of swap? Yes or no? If you think yes, raise your hand. If you think no, raise your hand. Okay, so you can kind of glimpse by the room that we have in the slide that this is not going to be the last example of swap that we're going to give today. So if you're not okay with this implementation of swap, can you tell me what's missing here? Move, exactly. We should move variables because in C++ we have move semantics. Moves usually does nothing for native types, but if you're working with containers or other more sophisticated objects, it's way, way cheaper than copying elements. So you should always move things rather than copying it if you don't need a copy. So yes, now we are moving our values. It's improved, but we still have a bit of slide here, so probably it's still missing something. What are we missing? Sorry? Forward? No, we are not missing forward. This is not the case for forward. Yeah, I would take concept as a possible issue because actually, if we want to move something, we are using features. And if we are using features on these types, we should be sure that these types support those features. Yes, we can check it with concepts, but I want to be old school today, so I'm adding enable if, and we are enabling the existence of the swap function on the condition that our type is move constructible and move assignable. Why move constructible? Because we are constructing the temporary variables. Why move assignable? Because we are move assigning other variables. So this is what we need to check. Do you think we are done? Raise your hand if you think we are done. Good, you can still see the room in the slide. So what's missing now? Yes, but I was hoping that was coming later. So there is constexpr, but not yet. What else? Decay? Nah, we can live without decay. You're doing something, exactly, no except. Now, something may go wrong while we move stuffs, and something may throw, or it may not if it's not throw. So we need to tell that swap does not throw exceptions if move construction and move assignment of our type does not throw exceptions while performing those operations. So far, so good. You already spoiled constexpr. In C++20, swap is constexpr. And it seems we reached the end, so we are done, right? Raise your hand if you think we're done. Okay, so what's missing now? You don't know what's missing. It's not really about this overload of swap, but you should always remember that in C++, there's something coming from C that we should not use, but we still use. Many people complain about. It has something to do with square brackets. C styles arrays. Guys, we need the overload for the C styles arrays. We can swap C styles arrays. I know this notation may give you some headache, but trust me, that's the right way to take a C style array by reference, believe it or not. Now, the no except is a bit uglier because we see twice no except is not a type. To work like this, the inner no except returns a bool, the outer no except expects a bool. If you are not okay with these complaints with the committee, I don't take complaints about it. Still you enable if on move construction and move assignment, and of course the implementation is slightly different, but yeah, we swap the whole array. Now we are done. Cool, we can swap. That was easy, right? Nice. I know what you're thinking. I should have studied Java. Let's move on. More swap. Now, after you learn to swap your way through code, we're in Italy, so I will tell the Italian sentence, but if I tell you i topi non avevano nipoti, you will probably think about palindromes, exactly. When we have palindromes, we check if the string or whatever is reversible. So let's check reverse. This is reverse as you will find it in the standard. I know it seems a lot easier than swap. And actually it truly is. And with reverse, we kind of learn the existence of iterators. We didn't know of iterators with swap. Yes, we learned a lot of concepts that gravitate around the C++ grammar. But now we're introduced to one of the most used design patterns of C++, which are iterators. With reverse, we learn of their existence, and well, the implementation of reverse is quite trivial. First and last iterators are incremented and decremented together, and we perform the swap of the elements while we go through them. After reverse, the only logical continuation is to find something clever to do with rotations. What does it mean to rotate a sequence? Let's imagine that you have this sequence, 1, 2, 3, 4, 5. Pardon my handwriting. I want to rotate it twice on the left. What do I get? I get 3, 4, 5, 1, 2. Okay? So this is a rotation of 2 elements on the left. Now, what does rotate do in the standard library? You provide the first iterator, the mid iterator, the last iterator, and it returns an iterator. The first iterator is the beginning of the sequence. The last iterator is the end of the sequence. So what you get is, this is first. Here we have last. And then the mid iterator, if you want to rotate by 2, this is what we do. We point to the element that we want to become the first element. The return value is an iterator that tells us where the previous first elements end up being. So far, so good. Are you still following me? Cool. Okay, so let's check the implementation. Okay, we checked some trivial cases, fine. And then we get these 3 if const exp, which kind of looks odd and doesn't seem they are rotating anything. In rotate, we learned that iterators in C++ may be of different types. We have random access iterator, bidirectional iterator, forward iterators, and other type of iterators that I will not pronounce. But let's check briefly this type. Random access iterator means you can go wherever. I give you an iterator, you can increment it, decrement it, adding 5, subtracting 17, you can do whatever. Bidirectional, kind of the same thing, but you can only go forward and backwards by 1 at a time. So you cannot decide, okay, I have a bidirectional iterator, let's go forward by 5. No, you need to increment it 5 times. And then we have forward iterators. Forward iterators means I can only go ahead 1 by 1. Why we need these ifs? Because given the kind of iterator that we are given, we may have a more or less optimized version of rotate. Let's check them one by one. The first one, it's the easiest. When you have random access iterator, it goes back to 3 reverse. We reverse from first to mid, then from mid to last, and then from first to last. If you do not believe this could be so easy, try it yourself. I assure you it's that easy. Now we want to return where the first elements end up being. So what we do is first plus last minus mid. Now we have seen reverse, and we've seen that reverse requires a bidirectional iterator because it was going forward by 1 and backwards by 1. So reverse is fine because random access iterators are more powerful than bidirectional, so we are good. Here we are exploiting random access iteration because we are incrementing an iterator by a value that it could be greater than 1. Okay? So now we need to address this issue for bidirectional iterator. And it's not that hard. You can do the first 2 reverse as before, and for the last reverse, you write a portion of the reverse by hand so that you stop when either first or last reached mean. When first reached mean, last is your return value. When last reached mid, first is your return value. And then you continue the reverse as before. And now the not so trivial part. Forward. Now forward is a bit clumsier to write, you can still do it. The most clever one amongst you may have noticed that this could be written with recursion. We have a first step, an exit condition, and then the recursion. I didn't want to throw it to a recursion just at the first slide, so I decided to unrecurse it. But yeah, that's the code. You can, again, trust me, it's correct. We are basically doing the following. 1, 2, 3, 4, 5. Let's say that this is begin, this is mid, and this is the end. What we are doing is, okay, we swap 1 with 4, we swap 2 with 5, we reach it 3, so we are moving, we are shifting everything ahead, so now this is begin, and this is mid, and we continue our swapping, and in the end, everything comes up together with a rotation. Again, you can check it by hand. It's a quite well-known algorithm. I didn't invent it. Clever people find that out. But yeah, it works. So after rotate, what do we have to do? Well, there are even more clever things that you can do swapping strings around. And one not very well-known algorithm in the STD algorithm header is next permutation. What next permutation does is returning the next possible arrangement of a sequence. Now, it may sound like dark magic, but this function is crazy useful, especially in unit testing, because it allows you to test all the possible permutations of a given series of inputs, and it's crazy how few people knows about it. How does this work? Well, here, first of all, we learn about the existence of predicates in C++. Predicates are just struct that can be called. So we have the overload of the invoke operator, or maybe our lambdas, or anything that can be invoked with the given parameters. In this case, next permutations requires a predicate that tells us if given two elements, which one is the smallest. So we need the lesser predicate. Also, we learn the existence of reverse iterator. Make reverse iterator creates a copy of the given iterator, but this iterator will behave in the opposite way of a standard iterator. If you do plus plus on first, you will go ahead of 1. But if you do plus plus on reverse last, you are also going backwards by 1, because the reverse iterator, when you do plus plus, it goes back by 1. Okay? So the reverse of last is the first, and the reverse of first is last. You can always go back to the natural iterator by calling dot base. So now that we have reverse iterator, we can iterate it in the other way. What the next permutation does, in case you never came across this algorithm, is that it goes to the next permutation that is the smallest, biggest permutation after the current one, which doesn't sound like something that can be comprehensive, so let's go with an example. Let's say that our sequence is composed by digits. So we have digits like 0, 1, 2, 3, 4, 5, etc. And that we have this sequence. 1, 2, 3, 4, 5. These are 5 elements of my sequence. Now, if you look at it, this is the smallest possible number I can write using these digits. Do you agree? Yes, okay. So if I want to get the next smaller number that I can compose with these digits, which one is it? 1, 2, 3, 5, 4, right? Okay, so this is the next number. 1, 2, 3, 5, 4. Now let's pretend that we are at these points of our permutation. We have reached 1, 2, 5, 4, 3. Which should be the next number of the sequence? 1, 3, 2, 4, 5, right? So how do we go? From 1, 2, 5, 4, 3 to 1, 3, 2, 4, 5. Well, it's fairly easy. We check backwards the first element that is not sorted in the sequence. So 3, 4 is greater than 3, so it's fine. 5 is greater than 4, again we are fine. 2 is not greater than 5, we are not fine. So 2 is our left element. Now we need the right element. The right element is the first element of the sequence that we've just skipped that is greater than 2. Now, since this sequence is sorted, and is sorted because we just checked it, we can use upper bound to find it. Upper bound is a function that does a binary search. So we're looking for the first element in the range reverse first left, so in 5, 4, 3, that is greater than what we choose as left. Which is the first element greater than 2 in this sequence? 3. So 3 is our right element. Now what we do is we swap 3 with 2, and we reach 1, 3. What we have now is 5, 4, 2. So what we do is we reverse 5, 4, 2, and we get 2, 4, 5. Cool? Are we okay? Perfect. How do we know that we have checked every possible permutation? When the sequence is fully reversed, this sequence is perfectly sorted the other way around, which means left is equal to last. If left is equal to last, we reverse the whole sequence, so we goes back to the smallest possible number, and we say we've checked all possible permutations. Okay? Questions so far? It's all good? Cool. And now the heap. Do you know what a binary heap is? Raise your hand if you ever heard about binary heap. Okay. Do you know what a binary tree is? Raise your hand if you know about binary trees. When does a binary tree is balanced? Yeah? Exactly, or in a simple way, when we do not have any hole going in a exploring the tree from left to right. So we have 5, we have 9, we have 3, 6, 7, 2, 1. If we delete 7, this is no longer a balanced tree because we have a hole. If we delete 1 and 2, it is a balanced tree because we have every possible node going left to right. But if we delete 7, 2, or 6, the tree is no longer balanced. Now, the cool thing about balanced binary trees is that they can be represented as an array, where the arrays contains the nodes from left to right, from top to bottom. Here we can see 5, 9, 3, 6, 7, 2, 1. The one below is not only a binary tree, it's a binary heap. What does it mean to be a binary heap? A binary heap respects another condition, is not only balanced, but every child node is smaller or respects a given condition with respect to its parent node. Here we can see the child nodes of 9 are both smaller than 9. Child's node of 7 are both smaller than 7. Child's node of 3 are both smaller than 3. This is a binary heap. What can we do with a binary heap? Well, we can apply our favorite function swap to do some cool things like pushing something on the heap. To push something on the heap, what we do is we add the element at the bottom of the heap. So we get our heap with the element that we want to add at the end of the heap. And what we do is that we swap the element with its parent until the parent becomes greater than the current one. And this is the code. As long as we have a parent, we check if the parent is bigger than us, we are done. If the parent is smaller than us, we swap our place with our parent. Now, I didn't say that before, but if you want to know your parent node, what you do is that you divide by 2 your current index. If you want to know your child node, you multiply by 2 your current index and add 1 or 2 if you want either the left or right node. So this is what a push heap could look like in STD. We have a push heap in STD. It works slightly differently than this, but this is a fairly good approximation, and it fits the slide. Then, in addition to push heap, there is another thing we can do. The other thing we can do is, let's say we want to remove the first element of the heap, 9 in this case. What we do is we swap 9 with the bottom element of the heap, and then we do what is called a percolate down, and the whole experience results in the pop heap. Now, the pop heap in the STD works slightly differently to reduce the number of branches. What we actually do is that we remove the top element, we place the bottom element at the top, and then we push that element bottom, but not checking the element itself, just checking the children. So in this case, you can see that first, imagine here, we remove the 9. So 9 is no longer here. What we do is we check the child of 9, the children of 9. We have 8 and we have 3. Which one is the biggest? 8. So we move 8 to the top. Now the hole is here. Which child node could fit the hole best? Between 7 and 5. 7, because 7 is the biggest. So here now we have 7. Here we have 8. And now here we fill the hole with 6, which is the element we remove. Now, we've been lucky that this sequence is fine, but what may happen is that 6 was not should not actually be in that position. So we need to push the heap from the first down to 6 to fix the fact that the 6 may not be in the perfect position. This may seem more work, but it's still a logarithmic cost function. And we do one less if in the while, which at the end of the day balances out with the number of swap. And given that a branch is more costly than a swap, it's slightly more efficient to do this way. Now that we know push and pop, we can create a priority queue. Priority queue is also a data structure that you can find in the standard library. And it works more or less like this. You have the possibility to push and pop something from the queue. The queue requires 3 template parameters. 1 is required, 2 are deducted usually. The first one is the type contained in the priority queue. The second one is the type of container that the actual queue is built upon, usually stud vector. And the third one is the predicate that we can use if you want a different way to compare your element that is not the lesser operator. It simply works like this. The slide is okay. Can you read it? Something odd? Oh, cool. We can go on. Perfect. So we have the priority queue. We have all the instruments that we need to tackle our first game today. The game we're going to look today is the game of 15. I'm sure you've all seen this kind of game. Raise your hand if you never played the game of 15. I'm sorry for you guys. You should at least know the rules. You have a 4x4 board with 15 tiles in the hole, and you should move the tiles in the hole, and your objective is to have an ordered sequence at the end. We are not actually going to play the game of 15 because it doesn't fit the slides, so we are going on an easier version, the game of 8. It works exactly the same way, but the grid is 3x3. You have 8 tiles in one hole, and you need to sort them from 1 to 8. Now, some few considerations before we begin. You should notice that the position of the holes in the row does not affect the final sequence. If I move the hole left or right, this sequence is always the same. Do you agree? Okay. So the only actual meaningful move is to move the holes up or down. Okay? Moving the holes left or right does not make sense. We only move it up or down. So those are the only 2 actions we care about. When we move the hole down, so we went from the board on the left side to the board on the right side. What did happen? If you look carefully, what happened is that we rotated the sequence that goes from the previous position of the hole to the next position of the hole on the left by 1. Do you agree with this statement? And what happens when we do the opposite? So when we go from the right board to the left board, again, we have rotated the sequence to the right by 1. Which sequence? The one that goes from the next position of the hole to the current position of the hole. So again, we are still working with swap, rotate, and reverse. Given these considerations, this is how we could create all the possible moves that I can do from a given state. So we represent our state as the 8 tiles that contains meaningful numbers and the index of the row where I can find the hole. Okay? I want to sort this sequence out. Now, what we want to achieve is, in result, to have all the possible combinations that we can have from a given state performing only one move. So only one move up or move down. How does this work? Well, first we need to have the operation of moving up and the operation of moving down. Move up, it's actually a free operation in once because we have to move up considering the row in the first column, second column, and third column. Now, I just recently notice that I can write this thing, which I think is amazing and terrible at the same time, but it works because that's an initializer list. An initializer list has begin and end, and so they can fit in a range at 4. So in this case, age will be evaluated first with 0, then with 1, then with 2. What we do is we create our first iterator at the position of the hole. We rotate our sequence from the position of the hole to the next position of the hole, as said before, and push back on our vector of results the obtained sequence. Cool with this? Something to say? Can I go on? Okay. Now, depending on the row of the hole, we can either only go down, go up and down, or only go up. Okay? So this produces all the possible states that follows the given layout of our board. Who knows the A-star algorithm? Less famous than many others. Cool, okay. So A-star algorithm is a graph finding algorithm. So it performs a search on a graph and is based on priority queues. What does this algorithm? I'll explain it briefly because we don't have a lot of time. It basically takes the most likely solution as the next element to evaluate. It takes all the children of that state, namely all the possible moves that I can do with it, and for each of the possible moves, evaluates which one is the most likely to be the next move. All those are inserted in the priority queue, and we remove from the priority queue, taking the one that is most likely to be the next one that we want to perform. And as you can see, the while we start from the initial move, as long as we have states to evaluate, we take the current best move possible from the one we can reach. If the solution, we create the solution. If none of those is in the closed list, meaning if none of those has already been evaluated, we take all the possible moves we can do and we push them in the priority queue. The priority is given by how likely it is to be the next state we should take. And we also add it to the closed list because we have evaluated that state, we don't want to evaluate it again. This is how the nodes looks like. It's not really relevant, just to give you the information. We have the current state. We have the parent node, which is the move we are coming from. Cost and heuristics are used by A-star, and that's how we determine if this one is more likely to be the next move that we should take. These are make node and make solution. Again, they're not really relevant. It's just for your information. Notable to look the make solution because at the end of the A-star, we are given the final node of the sequence. So the final move that brings us to the solution. And the parent node that I find are all the solutions that brought me there. Which means if I declare a vector and I push back to the vector all the states that takes me to the solution, I will have the steps that I have to do in reverse order. So before returning them, look who's there, again, our friend reverse. Again, swapping things around. So, perfect. Now we have the A-star that solves our small game of 8. We can create with the next permutation a program that solves every possible initial states of our game of 8. So we have a full solver for the game. This how would look like a possible solve everything algorithm. So as long as we can create another permutation of the sequence from 1 to 8, we create a game with the sequence. If the game is solvable, we solve the game. For each step of the solution, we print that state, and we say solved in n steps, okay? Now, you should know that not all configurations of the game are solvable. You need to have an even number of tiles out of position for it to be solvable. So we need to check if there is an odd number of tiles out of position, the algorithm is not going to find a solution, so we do not waste time looking for it. Okay, so it's demo time. Let's check, please. Okay. I know there is the background. Do not write feedback about this. Okay. Here there's white background. You can see we just received all the solution of this initial state. 1, 2, 3, 4, 5, 7, 8, 6 is the first permutation that is out of order, that is solvable. How do we solve it? Here you can see all the moves. In the first move, we clearly moved 5 up. So we move the hole on the right and move up 5 up. You can check all the moves one by one. I'm not going to do it. But you can see that at the end, we reach, this is way too much. We're almost there. One last move, and here we are. 1, 2, 3, 4, 5, 6, 7, 8. So we solved our small game of 8. Cool, now I can let it run for every possible combination, and I will have a full solution for our problem. I should have started from where we were. Let's go back to the demo. Now, the most if you paid attention, you may have noticed that I wrote this. Now, this thing doesn't exist in stud priority queue. Stud priority queue has a pop which removes the tops element but doesn't return it. And there's a top function that lets you inspect the top element. The issue is, if I want to move that element out, I cannot, because the top function is constant. I'm not allowed to modify it. That's cool. We are okay with that, because if I can change the element on the top, I could change its priority. And if I change its priority, then it's no longer a heap. So it's okay that we cannot change it. But I'm not okay with the fact that I cannot move it out when I pop it. So I had to add this pop out. Now, why does this pop out doesn't exist in the standard? Because the algorithm will look like something like this. Can you find the issue in changing the code in something like this? Exception safety, exactly, because this move can throw. And if this does throw, then what? I cannot reverse the pop heap because I have already removed it, but I haven't popped it back from my container, so I am in an inconsistent state. And so what I should do? We don't know. Now, there was a proposal to add a way to move out the element, and if this video reaches 5 likes, I would add to the proposal my personal consideration and a possible solution to avoid the throw problem. Basically, what would look like is that since pop heap, as we saw, use stud swap, and stud swap needs a temporary element to move something to allow the swap. We already have a temporary variables that contains something we moved in it. So if that thing could throw, it already threw when we moved it first. But what I'm doing is the first row puts it in the temporary variable of the swap, and that temporary variable is never touched again and is returned at the end. Since that move is already necessary to perform the pop heap, and since the return value is returned at the end, in C++17 we have guaranteed copy elision when we return the value. So that's not a copy, that's not a move, it's a copy elision. We already used the variable that was supposed to be our return type as the support value, as the support variable for the swap. Which means if it throws in the very first move that we perform. And when a move throws, you assume the element was not moved. So on a throw, we did not do anything. And if it doesn't throw, then everything is computed as follows. Again, 5 likes, and I will comment, and I will be blasted by the committee because I'm wrong. If I don't reach 5 likes, you get it as is. Thanks everyone for coming to the presentation.